Welcome to lesson number 4, navigation. You're halfway through the course. You know, IFR flight requires a higher level of precision as you navigate the skies. No longer able to rely on visual references on the ground and horizon, you must learn to navigate with avionics and instrument displays. In this lesson, we teach you all you need to know about the navigation instruments. You'll learn to follow and interpret the information depicted on the navigation instruments and study GPS navigation. Now, GPS navigation takes instrument flying to an entirely new level, providing unprecedented precision and situational awareness. In this lesson, we will cover these topics: NavAid classes, DME, VOR, HSI, ADF, RMI, RNAV and LORAN, ILS, GPS, and glass panel. Lots to cover in this lesson 4. Let's get ready with our first topic. NavAid classes. Please join your instructor for that discussion.
Let's get started with an old familiar system, the VOR. Okay, we're going to begin with NavAid classes. VOR navigation is the cornerstone of our navigational system and IFR flight. VORs are classified by service volume. We'll cover VORs in more detail later on, but because they're so important, we wanted to start this section by explaining the big picture. VORs have different classes of service volume useful for navigation, and you must understand these differences to reliably use VOR NavAids in flight. VORs are installed in several levels of strength based on service volume. These are the low altitude VORs, the high altitude VORs, and the terminal VORs. There are many approved charts and publications showing VOR classes. You can identify a VOR class by the markings that we're going to show you here. Let's take a look at some examples. The high altitude VOR is identified by a capital H. The low altitude VOR is indicated by an L next to it, and the terminal VOR is indicated by the letter T. So let's start with low altitude VORs. This illustration here shows a low altitude VOR. The standard service volume begins at 1,000 feet and extends upward to 18,000 feet with a 40 nautical mile radius. Below the 1,000 foot floor down here, the service starts from 0 nautical mile range at ground level and tapers up to the full 40 nautical mile range as it rises toward the 1,000 foot level of the service volume floor. Now here's the service volume for a high altitude VOR. First, notice it looks like an upside down wedding cake on a pedestal, with the pedestal being this part up here. The high altitude VOR provides the same type of information as a low altitude VOR, just with bigger boundaries. The first service volume tier is similar to a low altitude VOR in that it starts at 1,000 feet and goes out to 40 nautical miles. But there the similarity ends, as the ceiling of this tier is 14,500 feet. The radius of this service volume is larger at 100 nautical miles. From 14,500 feet to 18,000 feet, the third tier is largest with a radius of 130 nautical miles. This tier starts at 18,000 feet and goes up to 45,000 feet. It extends out to 130 nautical miles. You won't fly your typical general aviation aircraft above 18,000 feet very often. Only sophisticated aircraft and equipment are able to operate in the full range of this largest service volume. The service volume shrinks to a radius of 100 nautical miles above 45,000 feet and continuing up to 60,000 feet. Since most general aviation flight occurs below 18,000 feet, we fly routes where VORs are spaced less than 200 miles apart. This distance assures us of good navigational coverage. Now this is important as you navigate the midsection between the two VORs. Now let's take a look at terminal VORs. The shape of the terminal VOR is similar to the low-level VOR, but it has a smaller service volume. Terminal service VORs, they start at 1,000 feet, as we've come to expect. The ceiling of this lower-powered VOR is not as high. Its top is 12,000 feet. The terminal VOR radius extends outward 25 nautical miles. This type of VOR is located on airports with high-density traffic navigating to or away from the terminal airspace.
Okay, we're back in the studio for your first question of this lesson. To which maximum service volume distance for the OED VORTAC should you expect to receive adequate signal coverage for navigation at the flight planned altitude? Which of these, A, B, or C, in nautical miles is correct? Well, in order to determine this, we have to go to FAA Figure 30 to select some information. We can zoom in on a portion of this figure. We can see that the H stands for high altitude. We move on to our flight plan. We can see we're cruising at 8,000 feet. And here we see high, low, and terminal service volumes. At 8,000 feet, we're between the 1,000 and 14 5-foot level, which gives us 40 nautical miles. So back to our question, which is correct? Obviously, C is your correct answer. Okay, let's select another topic. And this time, DME. Back to your instructor in the classroom.
While slowly being replaced by GPS navigation, DMEs are still installed in many aircraft. They provide accurate distance information and provide an excellent backup for the newer GPS systems. VOR DME, VORTAC, ILS DME, and LOCALIZER DME navigation facilities established by the FAA provide course and distance information from co-located components under a frequency pairing plan. DME operates on frequencies in the UHF spectrum between 962 MHz and 1213 MHz. Aircraft receiving equipment, which provides for automatic DME selection, assures reception of azimuth and distance information from a common source when designated VOR DME, VORTAC, ILS DME, and LOCALIZER DME are selected. Now the acronym DME stands for Distance Measuring Equipment. Let's take a look at a typical DME radio, as you would find it in an aircraft. DME is integrated into a visual display or a stand-along radio. DME displays distance to the station and also calculates and displays time to the station and ground speed. The ability to display distance is critical in IMC or instrument meteorological conditions. This makes DME a critical tool. In recent years, however, GPS has provided DME information as a built-in function, replacing the need for a standalone DME. Listen for the coded identifier repeated every 30 seconds. If you cannot detect the coded identifier, then any DME signal is unreliable. DME measures slant range. Slant range is the angled distance from the VOR DME station to the aircraft and not the horizontal distance across the ground. At greater distances, this is not significant, but as the aircraft approaches the station, slant range error increases. Note the DME displays 2.0 nautical miles because the slant range distance is 12,000 feet. When the aircraft flies directly over the station, the DME display does not read 0. The DME reads the altitude of the aircraft above the station. So at 6,000 feet above the station as you pass overhead, your cockpit display reads exactly 1 nautical mile. Now as you pass overhead and fly away from the VOR, the distance display begins to increase again without ever going to 0. This is because it is measuring the slant range distance as you fly away from the station. DME slant range errors increase when we are close to or high above the station. Slant range errors decrease when the aircraft is further from the station or at a lower altitude. There are many instrument approach procedures, or IAPs, that incorporate DME arcs. A DME arc is when the distance information is used to fly a track that's a constant distance from a station. The procedure and techniques given here for intercepting and maintaining such arcs are applicable to any facility that provides DME information. Such a facility may or may not be co-located with a facility that provides final approach guidance. With an RMI, or radiomagnetic indicator, in a no-wind condition, pilots should theoretically be able to fly an exact circle around a facility. In actual practice, a series of short legs are flown. To maintain a 10 DME arc, you would proceed as follows. Now we have a 10 DME arc right here, and this airplane's right on the 10 DME arc, and that would be the RMI indication. When it goes wide, this would be the RMI indication, and when it's inside the 10 DME, this would be the RMI indication. With the RMI bearing pointer on the wingtip reference and the aircraft at the desired DME range, you maintain a constant heading and allow the bearing pointer to move 5 to 10 degrees behind the wingtip. This causes the range to increase slightly. Then you would turn towards the facility to place the bearing pointer 5 to 10 degrees ahead of the wingtip reference and maintain the heading until the bearing pointer is again behind the wingtip. You would continue this procedure to maintain the approximate arc. Now without an RMI, orientation is more difficult since there's no direct azimuth reference. However, the procedure can be flown using the OBS and CDI for azimuth information and the DME for arc distance. You would vary the amount of correction according to the rate of deviation and adjust as necessary according to the rate of correction. You would correct 10 to 20 degrees for each 1/2 mile deviation from the desired arc.
We have one review question for you on DME at this time. The question is, which DME indication should you receive when you are directly over a vortex site at approximately 6,000 feet? Which of these three is correct? Well, your answer is B. Distance information received from DME is actual distance and not horizontal distance. It's measured in nautical miles, and since 6,000 feet equals 1 nautical mile, the DME will show 1.0 above the vortex. There you have it. Moving to another topic. This time, VOR back to the classroom for that topic.
VOR is the primary navigational aid, or NavAid, used by civil aviation in the National Airspace System. The VOR ground station is oriented to magnetic north and transmits azimuth information to the aircraft, providing 360 courses to or from the VOR station. VOR navigation is a key component of navigation worldwide, even while GPS and other systems are becoming increasingly widespread and universally adopted. The acronym VOR stands for Very High Frequency Omnidirectional Radio Range. Now that's a mouthful to say, so the FAA abbreviates it VOR. When DME is installed with the VOR, it's referred to as VOR DME and provides both azimuth and distance information. The VOR components consist of a ground-based transmitter and a corresponding VOR receiver in the aircraft. The ground equipment consists of a VOR ground station, which is a small low building topped with a flat white disc upon which is located a VOR antennas and a fiberglass cone-shaped tower. The station includes an automatic monitoring system. The monitor automatically turns off defective equipment and turns on the standby transmitter. Generally, the accuracy of the signal from the ground station is within 1 degree. The ground-based component transmits an omnidirectional VHF signal. This signal contains phase, azimuth, or radial and identification information. This signal is then received by the aircraft's VOR receiver. The VOR receiver's audio output contains the ground-based identifier in Morse code. A separate instrument display shows the individual radial as it radiates from the ground-based transmitter. The courses oriented from the station are called radials. So check this out. Now, here's the VOR station. The VOR information received by an aircraft is not influenced by aircraft attitude or heading. Radials can be envisioned like the spokes of a wheel, on which the aircraft is on one specific spoke or radial at any one time. VOR facilities are orally identified by Morse code, or voice, or both. The VOR can be used for ground-to-air communication without interference with the navigation signal. VOR facilities operate within the 108.0 to 117.95 megahertz frequency band, and assignment between 108.0 and 112.0 megahertz is in even tenth increments to preclude any conflict with ILS localizer frequency assignment, which uses the odd tenths in this range. The airborne equipment includes an antenna, a receiver, and the indicator instrument. The receiver has a frequency knob to select any of the frequencies between 108.0 and 117.95 megahertz. The on-off volume control turns on the navigation receiver and controls the audio volume. The volume has no effect on the operation of the receiver. However, you should listen to the station identifier before relying on the instrument for navigation. VOR indicator instruments have at least the essential components shown in this instrument. The desired course is selected by turning the omni-bearing selector or OBS knob until the course is aligned with the course index mark or displayed in the course window. The course deviation indicator, or CDI, is composed of the instrument face and a needle that's hinged to move laterally across the instrument face. The needle centers when the aircraft is on the selected radial or its reciprocal. Full needle deflection from the center position to either side of the dial indicates the aircraft is 12 degrees or more off course, assuming normal needle sensitivity. If the needle is deflected to the left, you must fly the aircraft to the left to re-intercept the center of the course. And the same holds true if the needle is shifted to the right, then you must fly to the right to re-intercept the course. A series of dots, left and right of the deviation indicator, indicates left and right deviation, with each dot representing 2 degrees of deviation. Another component is the to or from indicator that's shown here. The to from indicator helps you know which radial will guide the aircraft to the station or the radial that will guide the aircraft away from the station. The nav flag warns of insufficient signal strength or an ambiguous radial display. So here's how it works. With the OBS receiver set to 360 degrees and the aircraft tracking directly to the station towards the 360 degree radial, the CDI needle is centered. When the OBS is set to 330 degrees, while still tracking towards the 360 degree radial, the CDI will indicate a deflection to the right, prompting you to correct right to track towards the 330 degree radial. Now, when the OBS is set to 030 degrees while still tracking toward the 360 degree radial, the CDI will indicate a deflection to the left, prompting you to correct left to track towards the 030 degree radial. Let's put this concept into motion. Now, this animation assumes no relative aircraft bearing position change and the aircraft tracking towards the 360 degree radial. As the pilot uses the OBS to select the 330 degree radial, the CDI moves to the right. As the pilot uses the OBS to select the 030 degree radial, the CDI moves to the left. Next, let's animate the to from indicator. Note, as we change the 360 degree radial and select the 180 degree radial, the CDI needle deflects first to the right and then to the left until centering. At the same time, the to from changes to from. During this transition, the nav flag briefly appears. Now let's do this once more. Note the indication as shown previously. The VOR frequency is shown on both VFR and IFR charts. Now, this example illustrates the Elizabeth City VOR frequency of 112.50 megahertz. Note that the VOR is co-located on the airport. A review of your VFR and or IFR chart legends provides additional information on the type of VOR and symbols. Now, here is a chart of the Elizabeth City VOR. Remember that radials always radiate away from the station and will be indicated with a from flag. A course to a VOR is always indicated by a to indication. Note in this example that when you navigate to the station towards the 340 degree radial, the inbound course is 340 degrees. And the course towards the 090 degree radial is 090 degrees. This example illustrates how you can get a very close fix by using two VORs and noting the from indication on each. The fix will be where the radials intersect. In this example, the intersection is on the 230 degree radial from the Sulphur Springs VOR and the 280 degree radial from the Quitman VOR. In the illustration, if we fly to the station on the 060 degree radial, the indicator shows a to indication. Or we can also fly from the station on the 240 degree radial and the indicator shows a from indication. Sometimes you want to track directly to the VOR. Our plane is showing a heading of 060 degrees, but note we're actually on and using the 240 degree radial, the one that's coming out of the station. Now, it's important to remember when you're tracking to or from a station, the heading on the OBS, in this case 060, must, assuming no wind or compass errors, agree with the heading on your heading indicator and magnetic compass. When your heading and OBS are in agreement and you have a centered CDI needle and a to indication, you are flying straight to the station. What if you get confused when you're flying to a station on a radial? Remember this, radials are always measured from the station. In this case, the 240 degree radial from. Yet, to fly to the station on that radial, we must fly the reciprocal heading, or 060 degrees. Reciprocal just means 180 degrees different, so the reciprocal of 240 is equal to 060. The position of the aircraft can always be determined by rotating the OBS until the CDI centers with a from indication. The course displayed indicates the radial from the station. The VOR indicator displays information as though the aircraft were going in the direction of the course selected. Actual heading does not influence the display. As the aircraft tracks towards the station, it has a to indication. The pilot tracks straight towards the station with a heading of 060, the reciprocal of 240. As the pilot passes over the station, the CDI fluctuates and the to from indicator switches to from on the VOR display. When flying outbound on the 240 degree radial, note the from indication that we have down here and the 240 OBS setting that you can see right here. This is because we are on 240 and we are flying from the station. Now we can bring this all together in actual use. Here we have an airplane navigating towards and intercepting the Elizabeth City VOR 270 degree radial. Note the 2 indication and the needle deflection. As the course to the 270 degree radial is intercepted, the needle centers. As the airplane passes the VOR and establishes the 270 degree radial, the flag will flip. To orient where the aircraft is in relation to the VOR, first determine which radial is selected. Next, determine whether the aircraft is flying to or away from the station. Look at the to from indicator to find which hemisphere the aircraft is in. Last, determine how far off course the aircraft is from the selected course. Look at the CDI needle deflection to find which quadrant the aircraft is in. Remember, aircraft heading does not affect orientation to the VOR. Lastly, let's cover the area of ambiguity. Now, here is our intended course. The area of ambiguity is represented by the bisection shown here. Note that on the area to the left of the VOR, a to indication will be presented. That's assuming you're flying to the VOR 060 degree radial. Therefore, all this area represents to the 060 degree radial. On the other side of the VOR, you will get a from indication since we're flying from the VOR on the 060 degree radial. In this graphic here, note the CDI is centered, and we have a selected heading on the OBS. As the aircraft flies directly over the station, neither to nor from is correct momentarily, and the nav flag is displayed. As soon as the aircraft is past the VOR, a solid from indication will be presented. Let's run this animation again. Note that the indication will be as previously indicated. The nav flag indicates that there is no valid to from condition. This means one of 3 things. Either you are directly over the station and the to from indication is about to reappear, or you are too far away from the station to receive a signal, or the station or system is not operating correctly. In the first case, you'll know in a moment if it changes or not. In the second 2 cases, you must turn on the audio portion of your VOR and identify that you are receiving the correct 3-letter Morse code identifier for the station. This Morse code identifier is your guarantee that the VOR is producing a reliable and useful signal. Next up, VOR testing. Regulations require you to operationally check the VOR every 30 days for IFR flight. We need to know how to check VORs for accuracy too. Let's go back to our VOR display. To test the VOR, use these steps to make the test accurate and official. Report the date of the test, any degrees of error, the place and the signature of the pilot making the test. This must be recorded in the aircraft logbook or some other record carried in the aircraft. The most accurate type of test is called a VOT accuracy check. The VOT is a ground-based signal located at airports across the country. To find the nearest VOT, go to the Airport Facilities Directory. In the back is a table listing VOR and VOT checks, listed by state. When you tune into a VOT test signal, you must confirm the correct frequency from the Airport Facility Directory and then set your OBS to 180 degrees. The VOR indicator must show a to indication, plus or minus 4 degrees centered of the needle. Now, an easy way to remember this is the acronym C182. C182 stands for centered, 180 degrees, with a 2 indication. If you remember this acronym, the reciprocal test becomes obvious. Centered, 360 degrees, with a from indication. Now, another way to check your VOR is by using a dual VOR receiver check. This requires 2 VORs, completely independent of each other in the aircraft. These VOR units may share the same antenna, but they must be 2 entirely separate navigational units. To accomplish this check, tune and identify the same VOR station on both systems. Then, select the same radial. The 2 VOR displays must be within 4 degrees of each other to be considered accurate enough for navigation. Here is the least accurate VOR check. While airborne, you can check your VOR using an airborne VOR check. First, locate the nearest designated airborne VOR checkpoint in the back of your airport facility directory. For this to work, you must locate your aircraft in reference to the designated spot on the ground, then set your VOR to the designated radial and fly over the checkpoint. When you do this, your VOR must center within plus or minus 6 degrees, while the aircraft is over the checkpoint to be used for navigation. Some VOR instrument displays show a second horizontal needle like we see here. So far, we've only talked about the vertical CDI needle and discussed how it's used as a course deviation indicator. The horizontal needle is called the glide slope indicator. It's used with the ILS, or Instrument Landing System. The ground component of an ILS transmits 2 signals, the localizer and glide slope signal. The signal received by the glide slope receiver and displayed on the glide slope indicator shows a high needle when you are below the glide path and a low needle when you are above the glide path. As you fly up towards a high needle or down towards a low needle, the glide slope indicator moves towards the center of the display as you align your aircraft with the center of the glide slope needle. The glide slope display provides precise vertical guidance information relative to the glide slope above the ground as it guides you down the approach to the landing zone. We discuss the glide slope in more detail later with the ILS, or Instrument Landing System, since the ILS integrates the vertical and horizontal needles on the VOR display.
Okay, let's tackle a couple of review questions. Now this question is going to ask you to refer to figure 95 in just a second. Which OBS selection on the number 2 nav would center the CDI and change the to from indication to a 2? Which of these, A, B, or C? Okay, here's nav 2, figure 95. Rotate OBS so the reciprocal of 170 degrees or 350 degrees is under the course arrow. This will cause the to from indicator or ambiguity indicator to indicate 2. The CDI now indicates the aircraft is 4 degrees to the right of course or on the 354 degree course to the facility. Rotate the OBS to 354 degrees to center the CDI. Back to our question, the answer of course then is C. Rotate the OBS until the reciprocal of 170 degrees or 350 degrees is under the course arrow, so the ambiguity indicator shows 2. The CDI now indicates the aircraft is 4 degrees to the right of course or on the 354 degree course to the selected facility. Rotate the OBS to 354 degrees to center the CDI. Okay? All right, next question. When using a VOT to make a VOR receiver check, the CDI should be centered and the OBS should indicate that the aircraft is on the, which of these radials? That's, the answer then is C. Tune the VOT frequency with the VOR receiver. With the course deviation indicator centered, the Omni bearing selector or OBS should read 0 degrees with a from flag or 180 degrees with a to flag. The question asks for on the radio, so you are 0 or 360 degrees from. So the answer must be C, 360 degrees radial. Okay, On to a new topic. HSI, and we ask you to join your instructor in the classroom to get that underway.
While not strictly a navigation system, the horizontal situation indicator, also referred to as the HSI, is unique in the way it displays navigation data from various navigation sensors such as VORs, NDB, GPS, and others. Okay, let's get into the heart of the HSI discussion. The HSI is actually two instruments in one. A heading indicator, as you can see from the compass rose display, and a VOR indicator, as you can see from the central needle with a head and tail pointer and a movable course deviation indicator in the center of the needle. The selected course is indicated by the yellow pointer. The heading indicator component shows magnetic heading at the top of the compass rose. The aircraft depiction is in the center. To fly the HSI, you turn the HSI selector knob until the top of the needle indicates your desired heading. If you turn to that same heading, then the CDI indicates the course you seek is to your left or to your right, and you can turn towards the desired course to intercept it at an angle. The tail of the CDI needle here represents the reciprocal of the heading selected with the CDI pointer. The best part of the HSI is the center visual depiction of a small aircraft and the angle of intercept that it shows for the selected radial. This gives you a great visual representation of your situation. The HSI also has a to from indicator and a glide slope indicator. This indicator drops or rises into the instrument face when properly tuned when flying an instrument approach using a glide slope. When the glide slope needle is centered, you are flying on the glide slope at that moment. With all of this visual information on one instrument, it's easy to see why it's called horizontal situation indicator. Now, another advantage of an HSI over a conventional heading indicator and VOR is that most are magnetically slaved. This means the HSI automatically seeks and holds magnetic north and does not need continual precession checks from the pilot. This slaving is accomplished through a remote magnetic sensor called a flux detector. It's typically located out on a wing and senses the Earth's magnetic field and automatically corrects the HSI. The HSI system also allows for slaving control. This lets the pilot manually correct a large amount of deviation on the HSI display. The deviation meter on the slaving control indicates the amount of correction applied to the HSI. Now let's use the HSI in flight to capture the 265-degree radial, for example. The top of the HSI compass rose shows our heading. After we've identified and tuned in the VOR station we want to use, we adjust the course deviation indicator until the head of the needle points to the selected course that we want to track to the station. The tail of the needle points to the reciprocal. This is the same as the radial as it radiates from the station. So now our radio and HSI are correctly tuned and set. By looking at the center of the HSI instrument display, we see a depiction telling us the relationship between the aircraft heading and the radial. If the CDI is deflected to the left or right of the head pointer, then that shows how to intercept the indicated radial. Usually you want to make this intercept angle at about 30 to 40 degrees, in this case 340 degrees. As the aircraft begins capturing the 340 degree radial center line, the deflected CDI begins to move towards the center, aligning with the head and tail of the needle. As this movement occurs, begin turning the aircraft towards the center line at a turn rate matching the needle's rate of movement so that the aircraft and the needle agree with each other on the 265-degree radial. It's a very satisfying feeling to roll out on the course center line at the same time the CDI needle centers. Note that you will have reverse sensing if you're flying the back course. You know you're on the back course if the HSI is set to the reciprocal of where the localizer is positioned. For example, if the HSI is tuned to 090 but the localizer is on the 270 extension, then you are on the back course and you'll have reverse sensing. We'll cover this more in greater detail later on.
Okay, let's tackle another review question. This time we're going to ask you to look at a couple of different figures. Question, to which aircraft position does HSI presentation C correspond? Which of these three? Of course, presentation C, we discover, is right there, upper left corner. And of course we have figure 96 here as well. HSI C is set up with the head of the arrow pointing to 90 degrees. With the CDI centered, the aircraft is obviously on the extended center line. With a heading of 90 degrees, position number 12 is the only one which would have that indication. Answer A is incorrect because aircraft 9 has a 360 degree, not a 90 degree. Answer B is also incorrect because aircraft 4 has a 270 degree heading, also not a 90 degree. So if we go back to our question and answer, the answer is C, position C for position 12. All right, let's tackle another topic here. And that topic is ADF. Back to your classroom with your instructor.
In the age of GPS, NDB stations are not used as often as in the past. However, they do still exist, and ADF systems remain in many general aviation aircraft. ADF systems are fun and easy to use. However, they're not as accurate as VORs and GPS. Even so, they remain a valuable tool in the pilot's navigating toolkit, as part of the world still relies on ADF navigation every day. ADF stands for Automatic Direction Finder. It consists of a receiver picking up low and medium frequency non-directional signals. AM radio signals are examples of this type of signal, and navigational aids known as NDBs or non-directional beacons also use this type signal. The system in the cockpit contains an ADF indicator display. This indicator always points to the station. That's all it does. It points directly to the NDB station tuned to the ADF. Pointing to the station is the simple way to use the ADF. This is called homing. The ADF can also be used to track. Homing is flying the aircraft on any heading required to keep the azimuth needle on 0 until the station is reached. Tracking is following a straight geographic path by establishing a heading that will maintain the desired track, taking into consideration the effects of the wind. So, check out this graphic. Regardless of the aircraft's location, so long as the NDB signal is sufficiently strong, the head of the needle will always point to the station. As the aircraft travels from right to left, again, the indicating needle always points to the station. There are three types of ADF indicators. They are the adjustable card indicator, the fixed card ADF indicator, and the RMI radio magnetic indicator. An important concept we're going to talk about is relative bearing. In this case, the relative bearing is 235 degrees, which is the bearing from the aircraft's nose clockwise or to the right to fly to the station. Relative bearing plus magnetic heading equals the magnetic bearing to the station. On the knowledge test, you'll be asked to provide the relative bearing. In example number 1, the relative bearing is 315 degrees. In example number 5, the relative bearing is 360 degrees. To find the magnetic bearing, you use this process. Assuming a magnetic heading of 320 degrees, add the relative bearing of 225 degrees to the magnetic heading. This gives us a magnetic bearing to the station of 545 degrees. Well, 545 is greater than the total degrees in a circle, so we need to normalize the magnetic bearing to the station by subtracting 360 from 545, giving us a magnetic bearing to the station of 185 degrees. Now the ADF indicator given to you on the knowledge test is somewhat simplified as shown here. The adjustable card ADF indicator simplifies finding the magnetic bearing to the station. For example, the aircraft has turned left from a heading of 020 degrees to 315 degrees. So what's the magnetic bearing to the station? Setting the ADF card heading to 315 degrees allows the needle to point to the magnetic bearing to the station of 190 degrees. The reciprocal magnetic bearing from the station is at the tail of the needle here. Here is the formula for computing the relative bearing to the station using an adjustable card ADF indicator. The magnetic bearing plus the magnetic heading equals the relative bearing. So here's an example to find the relative bearing to the station. The magnetic bearing is 190 degrees, and it's shown on the head of the needle. The magnetic heading found on your compass is 315 degrees. Subtracting 315 from 190 equals negative 125. So we need to normalize by adding 360 degrees, resulting in a relative bearing of 235 degrees. The relative bearing is only relative. It may not necessarily agree with the compass card and or the ADF pointer. Let's take a look at some examples of an adjustable card indicator. Now, indicator number 1 with a magnetic heading of 330 degrees has a magnetic bearing to the station of 210 degrees and a reciprocal of 030 degrees. Indicator number 2 with a magnetic heading of 315 degrees has a magnetic bearing to the station of 190 degrees and a reciprocal of 010 degrees. Now here is how to intercept a magnetic bearing. The desired bearing is 190 degrees. The magnetic heading is 315 degrees. The typical intercept angle is 45 degrees. So the intercept magnetic heading equals 190 degrees plus 45 degrees, which comes to an equal of 235 degrees. So note the markers on the ADF face. They're spaced every 45 degrees. Here's how to intercept the 180 degree radial to the station. The aircraft here is heading 315 degrees with a magnetic bearing to the station of 192 degrees. Turning the aircraft to a left intercepting angle results in a magnetic heading of 215 degrees with a magnetic bearing to the station of 188 degrees. Finally, the aircraft is on an inbound magnetic heading of 180 degrees with a 180 degree magnetic bearing to the station. Tracking to the station means we correct for the wind using a wind drift correction angle to maintain our course line across the ground. Flight instructors teach you specifically how this works. The knowledge exam asks us to solve a number of ADF-related questions using a formula. The last concept is homing. When you keep the ADF needle centered at the top of the ADF display, you are homing to the station. That's all there is to homing. It's simple enough, and it gets you to the station, but any wind may force the aircraft to fly a curved course to the station. This curved flight also means the course line continually changes, and in IFR flight, we want to fly consistent and precise course paths.
Okay, let's explore yet another review question. This one. We're going to ask you to refer to Figure 103 in a moment. On the basis of this information, the magnetic bearing to the station would be A, B, or C. Now the information on Figure 103 helps us out a little bit here. The magnetic heading plus relative bearing equals the magnetic bearing to the station. Shown here, the magnetic heading is 330 degrees and the relative bearing is 270 degrees. Therefore, 330 degrees plus 270 degrees equals 600 degrees MBTS. Now, that's a larger number than the number of degrees on the compass. We have to subtract 360 to get our answer. 600 minus 360 equals 240 degrees MBTS. Okay, we come back to our question. The obvious answer is B, 240 degrees. Okay, moving right along to our next topic. RMI. Your instructor and classroom await you.
Here's another navigation instrument, the RMI, or Radio Magnetic Indicator, also sometimes known as the Remote Magnetic Indicator. The RMI is a more sophisticated instrument with similarity to an ADF, but you won't see it in many general aviation aircraft these days. Most RMIs are dual needle RMIs, so you can show two indications at the same time. The double bar needle is usually the ADF needle. It points to the NDB. The single bar needle typically points to the VOR. The RMI is also slave to the magnetic compass. You can read your heading right here at the top, just like you can on a heading indicator. Let's take a look at an RMI. The ADF needle always points to the NDB, and the VOR needle always points to the VOR station. You can also use the ADF needle to point to a VOR. The same is true for the other needle. It can also point to either nav aid. That's what makes the RMI so useful. It points to two VORs or two ADFs or one of each. So here are two RMI facts to remember. First, the needle always points to the nav aid. And second, since the compass card is magnetically slaved, you can always read your magnetic bearing to the station directly at the point of the needle. Now here's another great way to use an RMI. If the needle is pointing to the VOR, then the tail of the needle shows you the radial you are on from the VOR. Simultaneously, the NDB needle indicates at the top of the needle point the magnetic bearing to the NDB. Now the DME locates the DME arc distance, and the RMI points a needle at the vortac transmitting the DME signal. By keeping the RMI needle pointed 90 degrees from your current heading, in other words, with the RMI needle pointed at the station beyond the aircraft's right or left wingtip, you can fly a perfect DME arc. Of course, you also want to scan your DME to confirm you're maintaining the proper DME arc distance. If you have a crosswind blowing the aircraft away from the station, then the needle must be slightly ahead of the wingtip reference, thereby turning you with a shorter radius, bringing you back on the arc course. If a crosswind is blowing you closer to the station, then you must keep the needle reference slightly behind the wingtip reference point, so your flight path can increase the radius from the vortac, putting you back on course with the DME arc line.
Okay, let's take a look at this question in review. We're going to ask you to refer to another figure in just a moment. If the radiomagnetic indicator is tuned to a VOR, which illustration indicates the aircraft is on the 10-degree radial, A, B, or C? Well, let's go to our figure, figure 104. VOR radials are from the station and are indicated on an RMI by the tail of the bearing indicator. Illustration 3, tail, indicates 10 degrees, which means the aircraft is on the 10-degree radial. Answer A is incorrect because RMI number 1 shows the aircraft is on the 115-degree radial. Answer B is also incorrect because RMI number 2 shows the aircraft is on the 315-degree radial. Of course, we go back to our question. The correct answer is C. All right, there you have it. Let's move to a new topic. This time out, RNAV and LORAN. Back to your classroom with your instructor.
Area navigation, or RNAV, was once considered as the most accurate navigation system. It's slowly being replaced by GPS navigation. RNAV navigation combined the range component of a DME and azimuth information from a VOR. An RNAV computer combined these two navigation elements and provides a very accurate position fix. Area navigation, or RNAV equipment, includes VOR DME, LORAN, GPS, and inertial navigation systems, or INS. RNAV equipment is capable of computing the aircraft position, actual track, ground speed, and then presenting meaningful information to the pilot. This information may be in the form of distance, cross-track error, and time estimates relative to the selected track or waypoint. VOR RNAV is based on information generated by the present VORTAC or VOR DME system to create a waypoint using an airborne computer. As shown here, the value of side A is the measured DME distance to the VOR DME. Side B, here, the distance from the VOR DME to the waypoint, and angle 1, VOR radial or the bearing from the VORTAC to the waypoint, are values set in the flight deck control. The bearing from the VOR DME to the aircraft, or angle 2, is measured by the VOR receiver. The airborne computer continuously compares angles 1 and 2 and determines angle 3 and side C, which is the distance in nautical miles and magnetic course from the aircraft to the waypoint. This is presented as guidance information on the flight deck display. The advantages of the VOR DME RNAV system stem from the ability of the airborne computer to locate a waypoint wherever it's convenient, as long as the aircraft is within reception range of both nearby VOR and DME facilities. A series of these waypoints makes up an RNAV route. In addition to the published routes, a random RNAV route may be flown under IFR if it's approved by air traffic control. RNAV departure procedures and standard terminal arrival routes are contained in the DP and STAR booklets. LORAN stands for Long Range and uses ground-based translating stations. LORAN was originally developed for marine use. A LORAN system installed in your aircraft must be approved in your aircraft flight manual and pilot operating handbook for use in navigation. It's not uncommon to find a LORAN in a general aviation aircraft, yet before using it for IFR flight, you must confirm in the aircraft flight manual or pilot operating handbook that it is approved. LORAN is being phased out and replaced by GPS, since GPS offers more precision, accuracy, and reliability.
Okay, back in the studio for a new topic. And this time out, ILS. Join your instructor to cover that topic right now.
When you fly into most major airports on an instrument flight plan, it's a safe bet you're using an Instrument Landing System, or ILS. The ILS system provides both course and altitude guidance to a specific runway. The ILS system is used to execute a precision instrument approach procedure. The ILS system consists of a number of components. The first component is the localizer. The localizer provides a horizontal position information similar to a VOR signal, but with a much greater sensitivity. A ground-based transmitter aligned with the center line of the runway broadcasts one radial aimed along the extended center line of the runway. It provides left to right information to the pilot who's approaching the airport along the extended runway center line. It's usually located 1,000 feet beyond the far end of the runway, providing azimuth or left to right information to the pilot who's approaching the airport along the extended runway center line. The normal approach is what's called the front course. It's 700 feet wide at the runway threshold. It's typically usable up to 18 nautical miles from the runway. The first 10 nautical miles of range provides about 35 degrees coverage from side to side. Beyond that first 10 nautical mile range, it's only useful about 10 degrees from side to side. Now, since the localizer only broadcasts one radial, you can have any radial set on your OBS without affecting the localizer indication. Some pilots, as a reminder of the runway heading, set the inbound course on the OBS. The localizer provides greater accuracy because it's 4 times more sensitive than a VOR. This means you must make very small wind drift corrections when you're reestablishing the center line on a localizer course. Keep your corrections between 2 and 5 degrees. Because of this increased sensitivity, the localizer is set to be between 3 and 6 degrees wide, depending upon individual airport installations. Now, just like a VOR, the localizer uses a 3-letter Morse code identifier for correct station identification and to ensure correct operation. You must always use this identifier before relying on the localizer signal. It's not a bad idea to leave that localizer ident audio tuned up and quietly playing in the audio background as a reassuring reminder of signal integrity as you fly the approach. Now, here is the localizer in the glide slope. Fixed distance markers are part of the ILS-2, and they're called marker beacons. Marker beacons provide range or distance information to the runway threshold. Your ILS approach plate states exactly how far each marker is from the runway, so when you cross a marker, you know exactly where you are on the ILS path. These low-powered marker beacons aim straight up, and they're located along the center line of the approach. They transmit their signal on 75 megahertz in a very narrow beam across the localizer course. When an aircraft flies through this signal, a visual and audio indicator in the cockpit is activated, providing the pilot with a precise distance mark at that location relative to the landing end of the runway. The furthest marker from the airport is the outer marker. Passing over the outer marker triggers a flashing blue light and a single tone repeated as long as the aircraft is within range of the outer marker signal. The outer marker is usually located 4 to 7 miles from the runway threshold and set at 1,400 feet AGL on the glide slope during marker passage approaching the airport. The next marker is called the middle marker. The middle marker is typically located 3,500 feet from the runway threshold, and it's set to activate when the aircraft is 200 feet AGL on the glide slope. The middle marker annunciator color light is amber or orange, and the tone is alternating dots and dashes repeating at a higher and faster frequency than the outer marker. Some airports also have an inner marker that's located at the runway threshold. The inner marker is indicated by a flashing white light and broadcasts an audio stream of dots only, reoccurring very fast at 6 dots per second. Now, frequently, a locator outer marker, or LOM, is used to further identify marker signals. They are low-powered, non-directional beacons co-located at the outer marker. Locator outer marker transmits the first 2 letters of the localizer 3-letter ID audio, and the locator middle marker transmits the second 2 letters. Now, let's go back to the glide slope and explain it in greater detail. The glide slope signal is provided by a ground-based transmitter located 750 to 1,250 feet from the approach end of the runway, and it's offset from the center line anywhere between 250 to 650 feet. The glide slope automatically is linked to the localizer signal, so you don't have to tune a separate signal to use the glide slope. Typically, the glide slope pathway is angled at 3 degrees above the horizontal ground. The depth of this beam is only 1.4 degrees deep, so it's very sensitive. The standard glide slope installation is set to have you cross the runway threshold at about 50 feet. It's important to intercept and use the glide slope at the published intercept altitude, as the glide slope can also put out several other pathways that are located above the true glide slope. These are called false glide slopes. They're faint, but if they're received and used, they can lure a pilot into the illusion they are correctly using the glide slope. Using a false glide slope brings the pilot to the runway threshold at an incorrect altitude, too high to make a safe landing. The published crossing altitudes for the marker beacons are good checks to provide you are using the correct glide slope signal as you approach the airport. Now, the glide slope indicator is normally combined with the localizer display as we see here. Generally, the crossing height at the inner marker is 50 feet. The glide slope is flown in a way similar to the localizer signal, just horizontally. If the glide slope needle is above the center line, like what you see here, you decrease your rate of descent so you can re-intercept the correct descent path. If the glide slope needle is below the center line, it's necessary to increase your rate of descent to re-intercept the glide slope. Because of the sensitivity of the glide slope, you need to make the smallest of adjustments to get back on track. Don't ever let the glide slope needle go to full deflection in either direction. If it does go to full deflection, the approach is so unstable, you must initiate a missed approach immediately and come around to try it again. Now, here are some other types of navigation facilities you may encounter. They're still in use, but they're increasingly hard to find. We've included them in the ILS section because they use a localizer type system that displays on your VOR. They are the LDA, or Localizer Directional Aid, and the SDF, or Simplified Directional Finder. We'll look at the LDA first. If you see an LDA approach, expect it to work similar to a localizer, but with some distinct differences. It may not be aligned with the runway or have straight-in landing minimums. An LDA also may not be located at the airport. The SDF, or Simplified Directional Facility, is similar to a localizer approach, but it's wider and it's typically fixed at 6 to 12 degrees rather than the narrower width of the localizer. The SDF also may not be aligned with the center line of the runway.
All right, this time we'll cover 3 review questions for you. The first one, when tracking inbound on the localizer, which of the following is the proper procedure regarding drift corrections? A, B, or C? Have a look at that. Okay, our correct answer is A. Drift corrections are small and reduced proportionately as the course narrows. By the time you reach the outer marker, drift correction is established accurately enough on a well-executed approach to permit completion of the approach with heading corrections no greater than 2 degrees. Okay, next question. Approximately what height is the glide slope center line at the middle marker, or MM, of a typical ILS? Which of these 3? Your answer is B. The middle marker, also the MM, indicates a position at which an aircraft is approximately 3,500 feet from the landing threshold. This will also be the position at which an aircraft on the glide path will be at an altitude of approximately 200 feet above the elevation of the touchdown zone. So the answer must be B, 200 feet. All right, our final question in this review. What are the main differences between the SDF, or Simplified Directional Facility, and the localizer of an ILS? The main differences, A, B, or C? And the answer is B. The SDF course may not be aligned with the runway, and the course may be wider than an ILS localizer course. The ILS localizer course width varies between 3 degrees and 6 degrees and is tailored to provide 700 feet at the threshold. Okay, moving along, yet another topic for us here. And this time out, we're on to GPS. Join your instructor for that discussion.
The newest and certainly the most accurate navigation method is the Global Positioning System, known as GPS. It's used in automobiles, the marine environment, and survey work, and it's becoming increasingly important in air navigation because it's so accurate and it works very well with all aircraft. Virtually all aircraft now have some sort of GPS system installed, and for those that don't have a permanent GPS installation, inexpensive and very accurate handheld GPS receivers are available. GPS consists of a number of navigational satellites in orbit around the Earth, each one transmitting a position signal. The GPS receiver in the aircraft computes its position based upon the signals it receives. For accurate position information, at least 4 satellites must be received. GPS installations on aircraft are found in the newer glass panel. They're found on newer aircraft integrated with flight and navigation functions. While classic installations are independent, they nevertheless provide identical accuracy and utility to glass panel GPS installations. The GPS satellite constellation provides a lateral fix with reception of at least 3 satellites. However, reception of at least 4 satellites is required to obtain an accurate 3D navigational fix. The signal strength must be at or above an approved acceptable level before determining a position. GPS accuracy and reception is provided globally. Since the GPS system is not immune from system outages, and to ensure the acceptable signals, GPS systems use RAIM, R-A-I-M, or Receiver Autonomous Integrity Monitoring, to verify GPS signal strength for navigation. If the RAIM test finds the satellite signal is unacceptable, a RAIM warning appears on the annunciator telling the pilot to use another form of navigation. The Direct To feature is the most common and easy to use implementation in modern GPS receivers. To use the Direct To feature, you must enter the airport identifier. Here we've got one, we're going to identify KAUO, or enter a name identifier, and the GPS computes a direct route to the destination and the fix. Now next up is Wide Area Augmentation, or WAAS. The WAAS is designed to improve the accuracy, integrity, and availability of GPS signals. WAAS allows GPS to be used as the aviation navigation system from takeoff through Category 1 precision approaches. The International Civil Aviation Organization, or ICAO, has defined standards for satellite-based augmentation systems. Unlike traditional ground-based navigation aids, WAAS will cover a more extensive service area in which surveyed wide area ground reference stations are linked to the WAAS network. Signals from the GPS satellites are monitored by these stations to determine satellite clock and ephemeris corrections. Each station in the network relays the data to a wide area master station where the correction information is computed. A correction message is prepared and uplinked to a geostationary satellite, a GEO, via a ground uplink, and then broadcast on the same frequency as GPS to WAAS receivers within the broadcast coverage area. In addition to providing the correction signal, WAAS provides an additional measurement to the aircraft receiver, improving the availability of GPS by providing, in effect, an additional GPS satellite in view. The integrity of GPS is improved through real-time monitoring, and the accuracy is improved by providing differential corrections to reduce errors. As a result, performance improvement is sufficient to enable approach procedures with GPS WAAS glide paths. The FAA is introducing more WAAS procedures all the time. While WAAS has strict equipment requirements, you're likely to find as many WAAS procedures as ILS. It'll be important for you to become familiar with these. It's also important to remember that only a properly installed and certified GPS receiver may be used for IFR flight. Popular handhelds and other GPS units may only be used for reference and never for navigation in instrument conditions. To use GPS for navigation, you must fly with an operational and certified alternate system in the aircraft as a backup if the GPS system becomes unusable.
Is there a different mindset that pilots need to use to operate an automated cockpit in addition to the basic stick and rudder skills?
Yeah, absolutely. The biggest challenge I see here is learning to put yourself in the role of being a manager of information rather than a doer of everything. And developing the ability to intelligently follow along as the systems do the work that you've delegated to them.
Okay, let's tackle a review question. During IFR operations using an approved GPS system for navigation, which of these is true, A, B, or C? And your correct answer is C. Procedures must be established for use in the event that GPS integrity outages are predicted to occur. These would show as RAIM annunciations. In these situations, the flight must rely on other approved equipment. This may require the aircraft to be equipped with operational NDB and/or DME receivers. Otherwise, the flight must be rerouted, delayed, canceled, or conducted VFR. Okay, good enough. Let's move on to another topic. And our last topic in this lesson, glass panel. Join your instructor for that discussion.
Technology brought the GPS to aviation and is now helping with another revolution, the glass cockpit. Once used only in large jet aircraft, glass cockpits are now used throughout all levels of aviation and increasingly are used in general aviation aircraft. Like any new tool, they have advantages, but they must be studied and understood before being used safely in flight.
Many of today's pilots are transitioning from steam gauge instrumentation to this, the glass cockpit. How is flight training evolving as a result of that?
Well, I think there's two schools of thought here. One school believes we should be teaching pilots to use these systems that we're now seeing in the cockpit and to put their trust in them. Another school believes we should be teaching those systems in addition to all of the old navigational skills that pilots learned in yesteryear: time, distance, rate calculations, fuel calculations, and whatnot. So depending on your frame of mind here, some people believe that flight training is getting simpler and some people believe it's getting more complex.
Steve, what's the basic idea behind the primary flight display?
Well, the primary flight display is easily one of the more interesting additions to the new cockpit. The first thing you notice about a PFD, or primary flight display, is that it's able to pack more information into a smaller space. What happened here is, as we started adding new systems to the cockpit, we couldn't have pilots craning their necks in all directions to gather the information they needed. So the PFD really integrates everything into one complete picture.
Let's start with some basic glass cockpit terminology. You'll hear the acronym EFIS, which stands for Electronic Flight Instrument Systems. EFIS units are increasingly used in newer general aviation aircraft. They're generally composed of two display units located on the left and right of the instrument panel. They provide spatial awareness, improved flexibility, it integrates information and program functions. The left side display, directly in front of the pilot, is commonly called the PFD, or primary flight display. While PFDs vary by manufacturer and model, they have many areas in common. Here's a typical PFD. Central to the PFD is a depiction of the attitude indicator like you see right here. To the left is a digital column of airspeed, and to the right is a digital display of altitude and vertical speed. To the bottom center is heading information, and often HSI information superimposed on the heading indicator display. To the right side of the instrument panel in a typical general aviation layout is an ND, or navigational display, featuring terrain map information, GPS information, and programmable features to allow you to navigate with electronic chart displays. The advantage is that once you understand how to operate these systems, they provide information intuitively and seamlessly. This reduces the pilot's cockpit workload and in turn creates additional safety by creating a high level of situational awareness. These advantages come with disadvantages too, of course. You must be familiar with the systems, how to program them, and how to make sure they're working properly. You must practice transitioning from them to the backup steam gauge instruments in case of a power failure. While EFIS systems provide greater flexibility and ability to integrate information and program many functions, you must spend time learning how to perform the programming and ensure that EFIS is being used properly.
Now, is it possible for a private pilot to move back and forth between the conventional six-pack and glass cockpit without compromising his skills?
Yeah, absolutely. I think the research is really clear on this topic. Any skill that you want to maintain proficiency at, you simply just have to practice regularly. That's certainly true of working with a GPS or autopilot. You've got to maintain proficiency with the button pushes and whatnot. And the same thing with scanning a six-pack panel. Basically, the bottom line is use it or lose it. Whatever you practice on a regular basis, you'll continue to be good at.
You may also hear some other glass cockpit terms. MFD is a programmable multifunction display that combines or alternates information such as power plant information with navigation as an example. Multifunction displays also allow more information to be displayed in the same instrument panel area, which is a distinct advantage for aircraft with limited display space on their instrument panels. ADARS, or ADAHRS, stands for Air Data Attitude and Heading Reference System. This system includes modules for flight instrument redundancy and can provide precise digital output and referencing of aircraft position, rates of motion, vector information, and acceleration data. SV is another term associated with EFIS and stands for synthetic vision. Synthetic vision combines 3D terrain information on a moving map display overlaid with navigational information from GPS and VORs or other nav aids. These new EFIS systems are found in many configurations and often include engine monitoring or a radio and transponder interface. If you have the opportunity, learn to operate an EFIS system and you'll be richly rewarded on each flight, since these EFIS displays are increasingly used on all aircraft.
Well, now here's an interesting question. What kind of backup instrumentation do technically advanced aircraft use should the screens go black?
Well, these technically advanced airplanes typically offer three conventional style gauges. It's an airspeed indicator, an attitude indicator, and an altimeter. The one thing I'd recommend to any pilot is get lots of regular practice using these things. Everyone thinks, well, these new systems are practically fail-safe and they only fail in 1 in 10,000 cases. But the thing you have to keep in the back of your mind is what if on some occasion you were today's lucky winner? So get lots of practice using everything in the cockpit.
Now, do you think that, for instance, a handheld GPS is kind of a good solution for a VFR pilot who's really wants some cockpit automation?
Yeah, absolutely. The navigation computer really is the heart of the cockpit, and these VFR-only handheld units really do offer a lot of features. You've got your GPS navigation, your moving map display, and in some cases, weather. So this is an excellent way for a VFR pilot to get many of the capabilities offered in an IFR-capable ship.
Great. Now, you probably have some recommendations for pilots who want to add a little bit of automation to their current cockpit. What would you recommend?
Yeah, absolutely. If you're buying individual systems, I would just say start out slowly. Get one system at a time and take your time mastering the use of the system and how to integrate it into your everyday way of doing things. Okay.
We'll try that again, and then I can follow up with what.
Go ahead, ask my question again.
Great. Now, Steve, you've probably got some recommendations to pilots, ways to automate their current cockpit. What would you recommend?
Well, for the pilot that's adding one system at a time to their cockpit, I would just say start out slowly. Take the time to get to know each system, how it works, and how to integrate it into your everyday way of doing things.
Now, as a pilot, what instrument would you be most interested in adding to the traditional aircraft? Yeah.
I think the typical first choice is the GPS computer and a moving map display. From then, many pilots are interested in the benefits of a traffic collision avoidance system or getting real-time weather information in the cockpit also. So any of these are available.
Now, Steve, with such an evolution in nav aids, how do you see land-based tools fitting into today's big picture with the availability of Google Earth and GPS so widely available?
Well, I don't see ground-based navigation going away anytime soon, and I think it's going to continue to be a valuable resource, both as a backup means of navigation and also as a means of training pilots to develop spatialization skills.
Great. Well, how do you see the ideal scenario for pilots today, combining navigation by pilotage and dead reckoning with electronic nav aids?
Well, I think the important thing here is to always have a second means of navigation going on, even if it's only in your mind. So when flying along an airway using GPS, I'll do a rough calculation of how much time it's going to take me to hit my next waypoint. That way I know if I type something wrong into the computer, I'm going to know when I get there. The other thing is using backup navigation techniques really can help increase your awareness. We did a study at NASA, took two groups of pilots. One group used GPS and just flew as they will. Another group used GPS and was asked to point out landmarks on the ground as we made our way across the flight. And what happened was, at the end of the flight, when we turned off everybody's GPS computers, the people that were providing the landmark information actually had a better awareness than the people who were just relying solely on the GPS.
So little standardization in instrumentation today. What are your suggestions for how a pilot can go about learning these instruments?
Well, for one thing, I have to say that in the future, we're going to need to do a better job of designing these computer interfaces. There are ways to design a computer interface that sort of makes the next step that you need to do, a little more apparent than what we're doing now. So there's certainly some room for improvement. For the time being, for the pilot, all I can say is you're just going to have to practice on a regular basis to get these keystrokes and button pushing procedures in your head and make them stick there.
Your suggestions for how pilots can manage the workload?
Well, the best advice I can give in regards to workload is get things done early, whenever possible, preferably on the ground. I like to think about all the scenarios that I might possibly get hit with that day and have a plan worked out for each and every one of them. You don't ever want to get to your destination airport, find out the weather is bad, and have it occur to you the first time that you might be going somewhere else. The thing that we have to remember here, the difference between airline flying and the kind of flying that we're doing here, is that those folks have 2 pilots in the cockpit, and with us, it's just us. We've got to do it all ourselves.
Steve, how should pilots pre-flight their navigation plans?
I would say always start with paper charts. Even if you're going to end up typing a series of waypoints into a GPS computer, it's a great idea to have a look at your routing and see what kinds of terrain and weather you're going to be flying through. I also like to do some basic time, distance, rate calculations, fuel calculations, and see where I'm going to stand at each waypoint. This way, it really does help maintain your awareness while the computer does its work.
Now, Steve, how do you think the next generation of navigation, communications, and surveillance will affect VFR pilots?
Well, that's a complicated question. I guess it all depends on how far-reaching these changes become. On the plus side, we're probably going to have improved ability to avoid other aircraft and hazardous weather. On the negative side, buying the equipment for all of these aircraft is going to cost a little money, and we'll also lose the option of squawking 1200 and flying anonymously if we're all issued ADS-B codes.
Now, Steve, the audience may not know you've written a couple of very helpful books, one called Cockpit Automation, the other Modern Airline Cockpit. Tell us about those books.
Well, what we're trying to do here is to help make a smooth transition from the conventional style cockpit to the more modern glass cockpit. And it certainly is going to be a challenge, and it'll take a while for the FAA to integrate relevant topics into the knowledge tests, the practical test standards, and whatnot. But for now, we certainly need some material out there for pilots to read and familiarize themselves with the equipment before they step into the airplane for the first time.
Well, Steve, we certainly appreciate your being with us. Dr. Kastner, once again, and hope to have you back in future programs.
Oh, thanks. I appreciate it.
Great. Now, back to our instructors.
Well, that's all for this section. Congratulations on learning about the diverse aspects of electronic navigation. You've completed study on a wide array of navigational systems to help you with your knowledge exam. I encourage you to take advantage of desktop flight simulators and computer-based tutorials available to allow you to familiarize yourself with the nav aids and practice the procedures we've discussed here. When you get in the cockpit for training, your flight instructor will reinforce and help you practice each procedure and others until you feel like a professional pilot as you navigate the skies. For Stenbach Communications and ASA, this is Rob Bremer, and it's been my pleasure to be part of your aviation training.